Good morning, dear student. In this lecture, we discuss the cyclic voltagram for potassium ferrocyanide redox couple. So, in earlier lecture, we already discussed theoretical part regarding to the cyclic voltammetry. So, in this lecture, we discuss how this cyclic voltagram is obtained for this potassium ferricyanide couple, okay, redox couple. So this is the cyclic voltagram for potassium ferricyanide couple. So if you see this graph, it is a graph of current versus potential. So on x-axis it is potential, and along y-axis it is your current. The current is again, it is your cathodic current, and the second is your anodic current. So positive current, it is denoted by cathodic current, and the negative current is due to the anodic. The current which is obtained at anode is known as anodic current. And if you see, this is the graphical representation, that is cyclic diagram for the current versus potential. And in this case, the potential is scanned from positive potential to the negative potential. That is, the potential is scanned from positive potential to the negative potential. So in this cyclic diagram, if you see what happened actually, so let us discuss some important points regarding to this cyclic voltagram for this potassium ferrocyanide couple, redox couple. So initially, uh, we know that in cyclic voltammetry, three different types of electrodes are used. One is working electrode, second is reference, and third is auxiliary electrode. So the first point is that the working electrode, in this case, is your stationary platinum electrode, and the reference electrode is saturated calomel electrode. So working electrode in the cyclic voltammetric study of this potassium ferrocyanide couple is platinum electrode, stationary platinum electrode, and the reference is saturated calomel electrode. If you see this cyclic voltagram, at initial potential of plus zero point 0.8 volt, so this is the potential, that is plus zero point 0.8 volt. So this is plus value, positive potential. So at initial potential, that is plus zero point 0.8 value, small anodic current is observed. So this is the point. So the curve, this is the curve where a small anodic current is observed, and this is immediately decreases to zero. It is a small anodic current is observed, and this is immediately decreases to zero as the scan is continued. As we scan from positive potential to the negative potential, a small anodic current is observed, and it decreases immediately to zero at the scan is continued, as the scan is continued. A negative current is obtained from the oxidation of water to give oxygen. So why we get this anodic current at this point A? Because negative current is obtained from the oxidation of water to give the oxygen. Then the second point is that no current is observed between the potential of plus 0.7 volt to plus zero point 0.4 volt. So up to this, from point this, that is from up to point B, let us consider up to point B, that is from potential plus 0.7 volt to 0.4 volt, there is a no current is observed. So no current is there, because if you consider no oxidizable or reducible species is present in this potential range. So this potassium ferricyanide cannot undergo reduction reaction at this potential, and therefore the peak current is zero. No peak current is observed because no oxidizable or reducible species is present at this potential. The potential is not sufficient to oxidize or reduce the potassium ferro or ferricyanide. So in this case, we discuss first the reduction reaction, means the potential, it is not sufficient to reduce the potential, or we can say that the positive potential or whatever the potential, that is from plus 7, 0.7 to plus 0.4. At that potential, this ferricyanide does not undergo reduction reaction, because the first reaction we discussed, that is the reduction. Ferricyanide takes one electron and convert into ferrocyanide. So and no oxidizable reducible species, because the potential at which the reduction is does not occur, and therefore no current is observed between plus 0.7 volt to 0.4 volt. When the potential becomes less positive, when the potential becomes less positive, and that is approximately plus 0.4 volt, a cathodic current begins to develop at point B. So up to this, so we discuss that from plus 0.7 volt to plus 0.4 volt there is a no current, but approximately from 0.4 a cathodic current is begins to develop from point B. So if you see, we get a graph, that is we get a peak from point B, that is the current is increases with decreasing the potential. That is, when the potential becomes less positive and we reach approximately to plus 0.4 volt, cathodic current is developed at point B, and this is because the reduction of potassium ferricyanide. This is because the potential reduction of whatever the current which is observed, or the peak which is observed, this is due to the reduction of this potassium ferricyanide. So this potassium ferricyanide undergo reduction reaction and convert into potassium ferrocyanide, and therefore the current is generated by the current is generated, it is known as cathodic current, because at cathode the reduction reaction is going on, and the potential at which the reduction is going on is known as cathodic potential. So you should remember this EPC and this EPA. What is this EPC? That is cathodic potential, cathodic peak potential, and anodic peak potential. So the potential at which the reduction takes place at cathode, therefore it is called as cathodic peak potential, and the oxidation takes place, it is called as anodic peak potential. So from point B, there is uh, the reduction of this potassium ferricyanide is started, and it is converted into potassium ferrocyanide, that is Fe, it is in plus 3, it is converted into plus 2. So the current which is obtained due to the reduction of ferricyanide to ferrocyanide, a rapid increase in the current is occur. So from point B, there is a slight reduction is start, but the rapid increase current is observed because we get a large peak. So we get a large current due to the reduction. A rapid increase in the current is occur in the region of B to C. So if you see, this is your C point. So rapid increase in the current is observed from point B to C, from point B to C, as the surface concentration of this Fe plus 3, that is ferricyanide, becomes smaller and smaller. So why? As there is a reduction of this Fe plus 3, means ferricyanide to ferrocyanide, and there is a rapid increase in the current due to uh, the decrease in concentration of this ferricyanide. So as concentration of ferricyanide is decreases, means it undergo reduction reaction, the current is more and more, and therefore a rapid increase in the current from point B to C is occur in the region from point B to C due to the surface concentration of this ferricyanide becomes smaller and smaller. Then the next point is very important. The current decay rapidly as the diffusion layer is extended further and further away from the surface, electrode surface. So what happened when there is a total reduction of this, when this Fe it is in plus 3, it will undergo reduction reaction. So when there is a conversion of total reduction of this Fe plus 3 to Fe plus 2, we get maximum current, and after that the rapid we can say that the current decay rapidly, means the current is uh, rapidly decreases as the concentration of this Fe plus 3 is there is no any concentration of Fe plus 3, means the current is decreases, because all this Fe plus 3 is converted into Fe plus 2 and we get a maximum current due to this reduction process. If we see next, that is at point D. At point D, there is a reverse of scan direction, and this potential is called as switching potential. So let us discuss one by one again the same point, that is up to point A, whatever the anodic current, it is due to the oxidation of water to give oxygen, and it rapidly decreases to zero as we scan the potential from more positive to the negative. Up to point, the region between A to B, there is a no current because no oxidizable reducible species is present. uh, at point B, the reduction of Fe plus 3 is start and we get maximum current at point C. And after that, when there is no Fe plus 3, no ferricyanide is there, then the current is rapidly decreases and we reaches up to this point D, where point D, it is known as your switching potential. The potential is switch, the scan direction is switch, and the current, however, to be cathodic, even though the scan towards more positive potential. That is, if you see this, we reach to this point switching potential. As we switch the potential, but whatever the current which is there, it is slightly cathodic, because we do not get directly the anodic current. We switch the potential, but the potential at which we get the current, it is cathodic. So what this point indicate, that the scan direction is switch. As we switch the potential, the scan direction is switch. The current, however, to be cathodic, it is not directly converted into anodic current, even though the scan is towards more positive potential, more positive potential. As the potential sweep in the positive direction, as the potential is sweep, that is, this is the switching potential. So we can scan from negative potential to the positive potential. So at this point, no doubt we can switch the potential, but current is slightly cathodic. After that, when you start, or we can scan the potential from more negative to the more positive, more negative to the more positive, the current goes to zero and then becomes anodic. So this is the point. So at this point, when we switch, it is not directly goes to zero, it having a certain a cathodic character, and then it reaches to zero, means that line, this is the line. So it reaches to that line. After switching the potential, it reaches to this line, and then it is converted into the anodic current. The anodic current is a result from the oxidation of ferrocyanide to ferricyanide. And whatever the current, that is, we get this E point, it is due to the oxidation of this ferrocyanide. This is your ferrocyanide, and it is converted into ferricyanide. This is your ferri, and it is converted into ferro. So this is just reverse to this. That is, we get a cathodic current. Same time, when the potential is reverse, we get anodic current. So during positive scan, that is, we can scan the potential from positive to negative, the species undergo reduction and we get a cathodic current. That is, we get a peak known as cathodic peak current, cathodic peak current. Similarly, when we switch the potential, we get anodic peak current, and the current is just reverse to that of cathodic current. So as the potential is sweep in the positive direction, that is, we can scan the potential from more negative to positive, and then the current goes to zero and then becomes anodic. So up to this point, when we switch the potential, it is slightly cathodic, it reaches to zero, and then it is converted into anodic current. Then it is converted into anodic current, and the current It is due to the conversion of this Fe plus 2 to Fe plus 3. That is the conversion of potassium ferrocyanide to ferricyanides. And this cycle is continue as we scan the potential from more negative to the more positive, and we get a complete voltagram. So this is all about the cyclic voltagram of potassium ferrocyanide redox couple. So you should remember the terms involved in this cyclic voltagram. That is, it is a graphical representation of potential versus current. So in this case, we get two types of current. One is called cathodic current, another is called as anodic current. The cathodic current is due to the reduction of ferricyanide to ferrocyanide, and the anodic current is due to the oxidation of ferrocyanide to ferricyanide. Then in this cycle voltammetry, we get a current in the form of peak, and therefore it is called as a peak current. And this point, the current is due to the reduction at the cathode, and therefore it is called as cathodic peak potential or cathodic peak current. Therefore it is called as cathodic peak current, while the current at anode is due to the oxidation, therefore it is called as anodic peak current. And this is your switching potential. At that point, we can scan the potential in reverse direction from more negative to the more positive. So it is very easy to understand the cyclic voltagram for this potassium ferrocyanide couple. In the next lecture, we will discuss the remaining practicals of our course. In this remaining practicals of our course, that is 434 section first. Thank you.